All right. Hello, everyone, to this OpsMill Uncut session number 3. My name is Wim Van Deun. I'm a product manager and solutions architect at OpsMill, and I will be taking you through this session. In this session, we will build up on the session number 2, which was basically explaining Infrahub schema and how we can create different schemas in Infrahub. Today, I also have 2 colleagues with me on the stream that are going to help me out. So the first colleague is Alex Gittings. Alex, do you want to quickly introduce yourself?
Yes, Alex Gittings, solution architect with Wim and Mikhail, and help customers and help the community members learn about Infrahub.
Thank you. And my other colleague is Mikhail. Mikhail, can you also quickly introduce yourself?
Yes, Mikhail Yeoman, also a solution architect and work with Alex and Wim, just helps supporting customers and community.
Thank you. Awesome. All right. So last time we have been talking about Infrahub schemas, and the topics that we have covered were mainly about how to create a schema, how do we define a schema in a YAML file, how do we then load that schema into Infrahub, and then we went into specific properties of that schema, like display labels, attribute kinds, relationships, how we could use generics to apply a system of polymorphism to the different models, how relationship kinds could influence the behavior of relationships in the UI, but also on the understanding of the scope of a relationship. One particularly important one there was a parent component relationship, which allows you to model, for example, an interface for a network device that belongs to that device. Basically, network interface can never exist by itself in a database, but it should always go along with a device. So that's where the parent component relationship came in quite handy. We talked about how you can define uniqueness constraints on the different models in your schema, and how we could use the HFID or human-friendly identifier to give a human-friendly name to an object that allows us to uniquely identify it within Infrahub. Then we also briefly touched upon schema migrations. So how can I evolve an existing schema, updating nodes or modifying existing attributes, adding new relationships, deleting relationships, that kind of thing. So today we want to expand on that, and some of the topics that we have mapped out for today are, first of all, we're going to start with hierarchical nodes, and then we're going to dive into some more, let's call them advanced concepts. First of all, we'll showcase what a computed attribute looks like. Then we'll dive into a new attribute that we've released, or it's a new feature that we have released in Infrahub version 1.3, which is the attribute kind number pool. Another feature that we have released in version 1.3 is the same parent constraint that you can define in a schema. So we'll cover that. Then we'll dive into templates, and last but not least, menu. All right, let's get started. So the first topic that we really want to discuss is hierarchical nodes. And hierarchical nodes are a way for you to define a hierarchy in the Infrahub schema. Let me try to zoom in onto this frame here properly. So the most common scenario where hierarchical nodes are useful are, for example, to map or define a location hierarchy. So typically we see that people want to map out their organizational structure into Infrahub, and hierarchical nodes are perfect for that. So they basically allow you to define this hierarchical tree. So what we can see here at the top is that we would have a country node, and that country node by itself could have child nodes, which are, in our case, or in the given example, they are cities. They could be anything you want, but in our case, we have chosen to have cities. So in this particular scenario, the parent would be the country, and the children of that country would be the cities. So basically, the country to city relation would be a one-to-many. So, and then basically you can expand on that hierarchy. So the city now by itself could become the parent of something else. In this case, we have defined another type, which could be a child, which could be a site. So a site in this case would be a child of a particular city. So again, from the city to the site, this would be a one-to-many type of relationship. So this would be the last child in the site, in the hierarchy, and that would basically stop the hierarchy. From here, you can then define other relationships to other objects. So for example, a particular site could have a relationship to the devices that exist within that site. So this basically hooks the device model into that hierarchy. So now we also basically have a way to figure out that a device not only belongs to a particular site, but we can also from here basically traverse the whole tree upwards to the root node, which in this case is the country. In Infrahub, we would call this ancestors and siblings. Right? So ancestors would basically be from a site anything upwards in the hierarchy. So the ancestors of site one would be city one and country one. And in the other direction, the siblings for country one would be city one, site two, city two, and site three. All right, so how do we start creating this in Infrahub? So we're
probably a question there, Wim, would be: is there like a limit to how many of these parent-child relationships you can have?
A limit in how big the tree can be, or?
Yes, correct.
There is no specific limit on that.
Yeah.
No, there's no specific limit on that. You know, and I'm not sure if we have ever really tested if we nested this 1,000 levels deep, but in theory there should not be any limit on this.
Yeah, and I know we do have some users of the platform that have like 6, 7 deep. They go from like region, Europe, then country, and then city, and then site, and then go even down to the building, and then for example, the rack.
Exactly.
Or room, for example. Yeah.
Yep. We have modeled some quite extensive hierarchies, and it worked. But again, those were not thousands of levels, of course, right? So
yeah, exactly.
But yeah, in theory, no limit at all. Okay. So what I'm going to first do is spin up an instance of Infrahub. We're going to use the same repository as before. So everything is exactly the same. By the way, we can probably also start sharing this repository after this session, so you can have access to all of the material that we are using today. So once this instance is up, we are going to load the schema that we had already defined in the previous time. And then once the schema is loaded, we will also load the object file, which contained some of the data that we had. All right. So object load data schema, and then we should be able to go to our instance, and we have the schema loaded. and we should have some device. So our first goal is to now extend the schema with a fairly simple location hierarchy. We want to add a site. A site is going to belong to a city, and a city is going to belong to a country. So the first thing that we are going to do is go into our repository and create a new file here. So I'm quickly going to copy a file from another location, and then we'll use that one. So this is going to be a fairly simple location hierarchy. So location hierarchies in Infrahub use generics. So we have explained generics in the previous session, but this is the first time where we actually see a requirement of the usage of generics. So whenever you implement a location hierarchy, you will have to implement a specific generic. They can be fairly simple. Let's go through it. So here we define a generic called location generic under the namespace location with a new generic. And what is really important here is on line 12, where we define that this is going to be a hierarchical node, meaning that this generic is going to be used to implement a hierarchy. This is going to allow us to identify really easily later on what the parents and the children of a specific node in the schema are going to be. Then we just define other properties of that generic in the schema like we did before, such as a name, a short name, and then we define things like the display level. Then to implement the tree itself, we have to create specific schema nodes that inherit from that generic. So in this particular case, we start at the root of our hierarchy, or the top level of our hierarchy, which in the first place is going to be a country. So we use the same namespace, but it's now a country. And this node is going to implement or inherit from our location generic, which is basically going to make it part of the hierarchy. As the parent of this node, we define the empty string, which can also be left out if I'm not mistaken. But this is basically a way for us to say this is the top of the hierarchy. By itself, a country does not have a parent anymore in our location hierarchy. Then the next important step is to define the children of a location. In this case, we're referencing a location city, which we had not yet, which we have not defined, or we didn't talk about that yet, but it's already referencing that. And then we still implement a specific attribute on this location country. So then we have the city, similar to the country it implements from the generic. It now defines the parent to be the location country, and by itself, it also has children, which are going to be the site. So we then define the site nodes, which again inherits from that same generic, making it part of that same hierarchy. And we just define a parent up here. So in here, we tie it back into the city. So now this is basically the schema that we would need to define this hierarchy in Infrahub. So let's load this schema into Infrahub. So the first thing we're going to do is create a branch. So I loaded the schema and the data initially into the main branch, just to get us to a starting point. But for this modification, we are going to make a branch. So, and just a reminder, this is a best practice. Whenever you start making schema changes, we always advise you to do that in a specific branch, so that if you decide that you don't want to use this schema anymore, or it's too hard to migrate away some of the changes that you have done, that you can just delete the branch and be back at basically at the initial starting point. So we created the branch, and now we are going to load the schemas within that branch. So while that is happening, I'm also going to copy over already another file for the next step. Yeah. So now we have the schema loaded. So if we switch to Infrahub and we go to our session 3 branch, we should now see new entries popping up in the menu. So we now have the country, the city, and the site. Now, that's not yet entirely useful. Let's add some data. So I'm going to use the infrahubctl object loads command to add some location data to the branch. Small typo there.
Probably might be worth showing that file just so people can see what it looks like, that data file.
Yes. I think we touched upon it briefly already last week as well. But in Infrahub, you can use object files, which basically allow you to define data in YAML files that you can load into into Infrahub, sorry. So in this particular case, we define an object file that at the top defines specific countries. In the data, you can see here that we define a country called France with a short name and a time zone. And for that country, France, we are going to define some children, in this case, cities. So we will define a city, Lyon, and a city, Paris. And each of those cities will also contain a particular site, location site, Lyon 1 and Paris 1. And we do the same for other countries. So that's very briefly and quickly what that object files look like. So when you load this file, it will create that data into Infrahub. So if I now refresh my page, you can see that some of that data has been loaded. One of the nice things about hierarchical nodes is that in the UI, we will automatically generate the hierarchical tree. So basically, what we defined in that object file was a country, France. The country France had 2 cities, which is the next level in the hierarchy. In our case, that was Lyon. And if we expand on Lyon, we can basically see that it has another child, which is a site, and that site is called Lyon 1.
Do you mind just zooming in that browser a little bit? There we go.
How much?
That's good. That's fine. Probably back one. Yeah, there. Perfect.
Bigger.
Yeah, that's
like
perfect.
This.
Yep.
All right. So that covers the location hierarchy. Maybe one thing we haven't really done is tie the devices back into this. So maybe that's a way we could quickly expand our schema. So,
before we get there, is there any other examples that we've seen that use the hierarchical nodes, for example?
We have seen people use hierarchical nodes in routing policies. That's one I recall from fairly recently. I'm not sure if you have seen anything else, Alex or Mikhail.
Not specifically, but you can do things like services, tying services to parents, for example, and there's multiple different ways you can skin the cat per se, but whether you do inbound, outbound relationships or use hierarchy to track dependencies as well.
Yep. All right. So basically what I'm now going to do is tie the existing device schema that we already had into this location hierarchy. So if we define a new relationship on the device, which is going to point basically to the bottom node of the hierarchy, which is the site. So it's going to be a relationship to a location site schema node. A device can only have can only be part of one site, so it's cardinality one relationship. We're going to make it optional because we already have an existing device in the database. If we would make it required, then it would not allow us to load this schema unless we would first delete the device. And we're going to make it a kind attribute. Then we likely want to do the same thing from the location. So on the location, let's define the relationship to device. Many, because a device can contain, a site can contain many devices. It's going to be optional as well. And it's going to be generic. Right, so let's load that schema. Okay, so now if we switch back to Infrahub, we should be able to see that at my Paris site, I now see a tab device. It's empty because I have not yet linked the device to that site. So let's quickly do that. So we have a device, device 3 that we created in the previous session. We'll edit it. Log in first. And we will link it to Paris 1. One nice thing that we have added in one of the previous releases that in this drop-down menu, when you want to select a site, Infrahub will detect that site is actually part of a hierarchy, and we will get this Explore tab in the drop-down, which allows you to, you don't necessarily have to filter the sites, but if you don't really know the site name, but you know where in the hierarchy it exists, you can basically navigate the tree like this to get to our site, which is really useful when you have a very big location hierarchy. All right, so now device 3 became part of Brussels 1, and you can basically see that on Brussels 1 on the device tab, we now have device part of the location hierarchy, basically. Okay, I guess that would cover the first topic of the day, which is the hierarchical nodes. So then let's dive into some of the more advanced concepts. What do you think, Alex?
I think
computed attribute first.
Computed attribute, yeah. Computed attribute for a device.
Okay. Let me think a little bit. So maybe something that we could do is create a computed host name or something like that, where we might have
it's a good
naming
one.
convention or something.
Yeah, definitely. We often see that people mistype things in names, so having the host name generated automatically when you edit parameters within Infrahub, it gets generated automatically, so any automation scripts can pick up that, and when you go to transforms and stuff later on, it's all generated automatically.
Okay, so maybe we need to explain first that there's actually two types of computed attributes that you can define in Infrahub. So the first one is a Jinja2 computed attribute, and the name kind of speaks already for itself. So it's basically an attribute where you can define a Jinja2 template.
Yeah.
Yes, a Jinja2 expression in which you can basically calculate the value of a specific attribute. What is nice about it is that it happens instantly. So when you create the object, it instantly calculates the value for that attribute, and you will immediately see that it is available. The downside is for Jinja2 attributes, if I'm not mistaken, that you can only traverse the relationships of a node. Well, the first level of relationship of a node. You can never access the relationship of a relationship, right?
Correct.
Yes, and then alternatively, we have the Python transformations. Sorry, the Python computed attributes, and those leverage another feature in Infrahub, which we call transformations. So transformations are basically the idea that you can apply some logic in Python code to data that you get out of Infrahub, and then you produce some kind of an output. So it's the same idea. You use some data that is part of your objects, and you can calculate whatever value you want based on that. The good thing about Python transforms is that it doesn't have the same limitation as the Jinja2 transform. So in Python, you can basically access whatever nested level of relationship you want, or maybe even data that is completely unrelated to the object itself. It's really up to you. There is no limitation on that. The downside, though, is that Python transforms are not necessarily executed immediately when you create the object, or when the attribute needs to be calculated. So basically, that calculation is happening in an asynchronous task. It happens in the backend, in the backend, and you have no control over when that will happen. We'll do it as fast as possible, but it might take a little bit more time. So I guess that's the big difference between the two. So I think for this example, we'll keep it simple and probably just stick to Jinja2 attributes.
I mean, I've seen people do some pretty interesting stuff with the Python ones, such as like get the peering information from peering manager and insert it into an attribute and do some pretty cool stuff, which is really interesting.
Yeah, in it, I was trying to remember, but I do remember seeing a case where someone was really calculating based on specific things what specific metric would be applied to a specific route. So you could basically influence based on data what the specific metric of a route would be, whether it becomes a preferred one or not, and stuff like that. Yeah, you can do pretty fancy stuff with it.
Yeah, it's interesting.
So this introduces some new things that we need to talk about. So it's just basically we define an attribute like we have always done. In this case, we'll name it hostname, and we're going to make a text attribute. We can use a new property here called computed attribute, and we'll have to define what type of computed attribute it is. In this case, a Jinja2 computed attribute. Then we're going to define the template, and here it gets a little bit interesting. So now we can basically access the attributes and the relationships of this particular node that we're working on. So maybe the hostname could be taking into account the site that it's part of, and then maybe the role, and then maybe the name that we defined initially. Let's tie all of those together with dashes, and then something like that. I think that would be working already.
Sounds good.
So the way we access the relationship in this template of this node is basically by using the name of the relationship. So I'm going to use the site relationship here. Now, from the site, I want to use a specific attribute. I'm not sure if you remember, but we did define a short name on each member of the location hierarchy. It's actually was defined on the generic. So we can access the attribute of the relationship by prefixing the relationship name with a double underscore, and then the attribute name. In our case, that was short name. And then we want to access the value of that attribute. So this would allow us to basically get the short name value of the site for this particular node. Now, maybe a good idea to use a Jinja2 filter here. In this case, let's use upper to upcase all of the characters in the value of that attribute. Actually, I do think we have quite a few Jinja2 filters that we make available by default, right? If I'm not mistaken, we also include some of
the netutils library. Yes.
Not
so there's handy things like MAC address conversions and ASN conversions in there that are very helpful. So if you need like the dot notation or the longer number version, then you can you get you can use those netutils filters for that.
All right, so we defined two more things that we want to be part of our computed attributes. We want to use the role attribute of this particular node. So the way you access an attribute is exactly the same as a relationship. So we use the name of the attribute, and then we want to use the value of that attribute, and we're going to pass it into the upper filter as well. And then we do the same thing for the name, which is an attribute. We use the value and we upcase that as well. Okay, one requirement is that we define this attribute to be read-only. A user should not be able to modify a computed attribute. And in this particular case, we also want to make it optional because we have already defined this attribute. Oh, well, we already have device nodes in our database. So to make the migration work, we need to make it optional.
So just for our customers, like for the users here, it's optional because there's already data. If you didn't have data, it could be optional false, so it is mandatory. But because we've got data, we need to migrate it. So optional true, push that schema, and then once the schema is pushed, you could then change it to mandatory, for example.
Exactly. Thank you, Alex. Let's load the schema. Okay, so now hopefully if I refresh my page, yes, it already happened. We can now see device 3, which has a new attribute called hostname. This attribute is something I cannot modify, right? If I click on the edit form, it will not show up here, so I cannot modify it myself, but it was calculated by Infrahub. So PRU01 is basically the short name that is defined on the Brussels site, uppercase as specified in the template. Then we have the role of the device uppercase, and then the original name that we defined, in this case, device 3. So now if I change the role to firewall, then we should see, if I refresh the page, that now my computed host name has been updated. So it happens instantly. Okay, that's what computed attributes are. I think Python computed attributes are exactly the same, but you use Python logic, a Python transformation, a Python script, basically, in which you can calculate a value of an attribute based upon whatever you want. But the difference, again, is that it's an asynchronous task that happens in the system. Nice. We're at the half hour mark, so we still have half an hour to go. I think we should be good. Any
I think so.
other new questions?
I don't have any, but Mikhail, does the community got anything?
There is one question that I'm attempting to kind of flesh out a little bit, but the question is, can I only use, or for computed attributes, can I only use it to get, or sorry, for get requests, or can I use it to set something? For example, limiting the bandwidth going through an interface, or even setting a protocol. So just attempting to clarify setting something with an Infrahub or an external system.
Okay.
So we'll probably revisit that a little bit later, unless y'all have something to add to that at this point.
I think technically you could.
Yes.
An external system or even an internal system, right? You're in, I mean, with Python attributes, you're in Python land and you can do whatever you want, right? So we cannot really restrict you on anything. Yeah, I don't think we have used them in that way, but you can. Absolutely.
Awesome.
All right. So attribute number pool. So this is one of the new features that came in Infrahub version 1.3. And it's basically a combination of multiple features that already existed. So previously in Infrahub, you had already the possibility to define what we call resource managers. So you could basically define a number pool, which is basically a way to allocate the next available number in a pool that you define. And you can link that to a specific attribute on a node in the schema. So what that would allow you to do is when you create a new node of that specific kind, you would be able to select the number pool for that particular attribute so that it would allocate the next available number out of that pool for you. The downside of that feature is that you had to create those pools individually, and there was no way to force that somebody had to use the number pool. And that changes with this new feature. Well, the old mechanism is still available. There's no change to that, but attribute kind number pool is a feature that allows you to create an abstraction on top of it. So basically, it allows you to describe in the schema that you want to use a number pool for a specific attribute. And then you can basically abstract the fact away that you have to create a number pool. Infrahub is going to do that for you in the backend and link that number pool to that attribute so that whenever you create a new node of that kind, that attribute will be automatically populated with the next available number value within that pool. And similarly to how it works for the traditional number pool, this also works across branches and the same way that resource managers always work. So one way I've customers seen doing this is sometimes they want to create some kind of a customer model, and that customer may be linked to specific services on the network, right? They consume specific services from you. So I want to keep track of that. And maybe that customer also needs to be Now that's maybe a piece of data that you want to synchronize to other systems in your organization, and that other system requires that each customer has a unique number or something like that. So maybe what we could do is create a quick schema for a customer and use a customer a number pool attribute here. Sorry, let me first. I didn't mean to show this already, so let's ignore that for a moment. So we define a very simple model called customer. A customer is going to have an attribute name, which is going to be of kind text, and then we'll define a customer ID. This customer ID attribute is going to be of kind number pool, which is basically a number attribute, but there's going to be a pool tied into it. So at this stage, you can basically define that, there's going to be a number pool that is attached to this attribute, and Infrahub is going to create that number pool for you. And whenever you create a new object, a customer object, it is going to automatically allocate out of that number pool. It needs to be a read-only attribute. Sorry, you wanted to ask something, Alex?
I was going to say, actually, we could probably actually show parameters as well in the same use case to start the number not at 0.
So I think the right parameters.
It's start range.
But anyway, yes, and end range. So it's a number pool, and here we want to define some additional constraints like start range. So we might want to start at 1,000, and end range is going to be, I don't know, 100,000. So that's what this should do. Let's load that schema.
Just thought we'd get that in there to add the parameters, as that's new in 1.3 as well.
Exactly. So actually, it's parameters is not specifically tied to a number pool attribute. It is more generic for other attribute kinds as well. So for example, on a number attribute, you might want to define some additional constraints as well, like a min value and max value. Previously, you could already do that, but we didn't really have a good way to define, for example, something similar as well on text attributes. So what we did in 1.3 is we implemented this parameters key in the schema that you can define on attributes. And depending on the type of or the kind of attribute that you use, you can use different parameters to influence some extra constraints. On a number would be min value, max value. On a string, it could be the length of the string or a regular expression to which the string needs to match. So did I now load my schema?
Yep.
I think I did, right? Okay. So actually, the number pool already shows up. So we loaded the schema, and we can see now that Infrahub has created a number pool resource manager for us already. The name may not make a lot of sense to you, but it's basically the schema node that it is linked to, and then the attribute with a specific UUID that allows us to tie those two together at the database level. We cannot get the resource full yet because I properly did something wrong. I don't know. But let's create a new customer. So we now have the customer schema available, and we can create a new customer. So let's create a company called OpsMill. And if we do, we can see that the first customer ID that was allocated is 1,000. And if we create a new company, I don't know, let's do Cisco, we should see that Cisco now gets the next customer ID, which is quite a change from before, because before we would really have to manually select that we wanted to use a number pool for this attribute. And I'll go back. I'm not sure what's happening here, but normally the number pool should show up, and it should show all of the numbers that it is already allocated and to which objectives have been allocated to. Maybe the demo gods are not that friendly for me today. But yeah, that's number pools. So number pool attributes, where it really gets cool actually is when we start combining that as well with computed attributes. I'm not going to make this too long, but if we now add another computed attribute here, which could be the calculated name of the customer, like very similarly to before, we use a Jinja2 template here. We're just going to use the name of the customer and append the automatically allocated value. So if we now load this schema, final. Then we should actually see that the calculated name comes up. So now we have used the combination of those two features, so computed attributes together with a number pool attribute. So this makes it really powerful. Okay, next one, same parent constraints, another feature that was introduced into version 1.3. So a scenario where we have seen this come up is, I think a good one is let's say you want to model a new type of interface on a network device. Could be a lag or a port channel. So when you define that in the schema, you could just create that as another type of interface, maybe using a generic. And then a lag interface should probably have a relationship to the member interfaces, right? The interfaces that are part of that lag or that port channel. But the problem that we would start to see occurring is that the lag interface is linked to a device. So we would only want to be able to select member interfaces on that same device for a regular lag, right? We should not be able to select interfaces from another device into a lag. And this is really what same parent constraint allows us to do. It allows us to define that a relationship from a specific node, or when you add a related node to a relationship, that both those nodes should have the same parent. So this comes, it actually ties back into what we discussed in the previous session, which is the parent component type of relationship. So let's try to model that. So if we go back to our existing device, we will see that it has a relationship to a generic, which was our infra interface object. And then there were two types of interfaces that we created that we can basically relate to, the layer 2 interface and the layer 3 interface, both inheriting from that interface generic. What was really important here was that on that relationship from the device to the interfaces, we define that they are components. And if we look at the interface generic, in the other direction, we define them as parent. So now what we want to do is add a new type of interface. Let me get to that quickly. All the way at the bottom. We're going to define a new type of interface called a lag interface. We're going to inherit from that same generic. So basically, this means we will inherit that relationship to a device, and that relationship is going to be of type of kind parent. And in the other direction, we will also get a relationship which would be of kind component. So basically, making the interface part of the same a component of the same parent, which is a device similar to the other interfaces. So then on that lag interface, we define a new relationship, which we call members. And those members are going to be other layer 3 interfaces. Now, it could be many of them, right? We could have many member interfaces. But what is really important in this new keyword here, common parent device. So, and what that really allows us to do is basically define that any object that we want to add to this relationship, being an interface layer 3, needs to have the same relationship of kind parent, which is named device. So basically, this is a declaration that says you can only add a member interface to this lag interface that is part of the same device that I am part of. And it's a bit hard to see because we use a generic here, but it actually points at this relationship, which both the interface and the lag interface have. Okay, so that should be it. I don't think we have to do anything else here. So let's add that schema. Okay, so now if we go here, we should be able to create layer 3 interfaces, lag interfaces. Perfect. Maybe let's add a new layer 3 interface to our device first. Let's call it Ethernet 4. And it's going to be device 3. Well, so now we have two layer 3 interfaces. Maybe another thing I could do is actually quickly create another device 4. No platform. Let's just put it here. Made a typo, but it's not very important. Let's add another layer 3 interface, Ethernet 1, to this device. So now we have multiple interfaces on multiple devices. So now what we want to create is a lag interface on this device 3. So we find port channel 1. And we want to make it part of device 3. So now we have our port channel defined, and we can see that there is no members yet on this port channel. So now we want to add member interfaces, and what we can see in this form that automatically this drop down is locked down. Like you cannot change the device here. So basically, we understood that this interface port channel 1 is part of device 3. And because of the common parent constraint that we have defined on that relationship, we understand that only interfaces on that same device should become allowed to become a member of this port channel. So now you can see that we have only 2 candidates available here, which is exactly right because we had interface Ethernet 3 and Ethernet 4. And unfortunately, we haven't defined display labels for them, but then their proper name should show up here. So you can see device 3, Ethernet 3. And then let's take the second one, which is device 3, Ethernet 4. Notice that there is no more candidates like the other layer 3 interface that I created on device 4 is not there at all. So that's what the same parent constraint allows us to do. So it's really an addition on top of the parent component type relationship that we already had. Okay, so that checks off that one. Which one would be the most useful? We still have a few minutes.
We did have a question, I believe, just for what you just showed. But with clicking on one field in the navigation bar, can I have multiple fields there, or is it always the same? Whoops.
Sorry, can you repeat that question, Mikhail?
It disappeared on me. Let's see. So with the clicking on one field in the navigation bar, can I have multiple fields there, or is it always the same as the one I just clicked? Didn't figure out how to group multiple entities.
I'm not sure if I understand that question. Do you understand it?
I'm not sure if this might be related to like having the parent kind on an attribute to where you could select even further, the qualifications. But I am not quite sure. I'll have them elaborate on that.
All right. Let's try to. Any other questions, Mikhail, or?
One just came in. Can you use parent constraints against multiple parents?
Parent constraints against multiple parents. I would probably need an example to answer that one. Unless somebody has an ID.
Yeah, I'm not sure potentially with that one. That may be one we have to also dive in. I do want to, I don't know if we covered it, but when do computed attributes get updated, right? So initially when you create them, the Jinja attribute gets rendered right away as where the Python is async, but how do those get updated?
So you mean when we change, like, I think we did that throughout the demo, right? But let's do this one. This is actually perfect because we have a typo here. So it's missing an E here, so the computed name is wrong. So when I edit my device and I added this attribute, we understand that the computed attribute needs to be recalculated. So we will do that immediately because this is a Jinja2 attribute. Jinja2 attributes, computed attributes get calculated immediately whenever they need to. So when there is an update to an attribute that affects that computed attribute, we will immediately recalculate it. So you can see that after I refresh the page, it was immediately updated. For Python transform or Python computed attributes, that's a little bit different. Again, they are executed asynchronously in the backend, and we have no control exactly when they will execute, as fast as possible, let's say. So that's a downside of Python computed attributes compared to Jinja2 attributes. But yeah, the task to do the recalculation will be submitted immediately, and then it will be executed as fast as possible, basically. So it really depends on how many tasks are currently being executed by the system, and yeah, this one just goes into the queue, let's say.
Awesome. For the multiple parent constraints, for that one, the example is potentially filtering port channels on a certain device, and that's also part of a certain tenant. So I think if a device has a parent relationship, right, to a tenant, do we support that today?
So I'm just thinking, right? Like, so it should be a tenant is linked to a specific port channel.
I think it would be from the device. So we say it must be the same parent for the device level, but can we go up another level to say like maybe the device is a parent relationship to a tenant, and then could we filter based on that?
I'm failing to still understand it. Like, would you want to add a member interface to the port channel, which is part of a different device, but the same tenant? Is that what you want to be able to define then, or?
Let's see. I think from my understanding is to say that, I guess with that example, it's still going to be at the device level, correct? But I think maybe what they're trying to get at is that you want to be able to say they also have to be part of the same tenant, like the device must be part of a specific tenant. I'm not sure if the...
Yeah, but if you define the same parent constraint on the, I mean, if a device is part of a tenant, then inherently the interfaces are, you know, not directly but indirectly related to the same parent through the device. So the same would happen with the port channel. So if you define the same parent constraint on the device, you create the same effect, right? Like, because the device is part of the tenant and the interfaces as well, it means that, you know, if you define the same parent constraint, the interface will always be part of the same device, which is part of the same tenant anyway.
Yes. Okay.
So maybe we fail to understand that use case. And you know, if you want to elaborate on it, feel free to reach out to us on Slack. We're more than happy to assist you or help you further. But I guess we need a little bit more clarification to properly understand what you really want to do here.
Yes,
okay.
And I would say that's probably the same for the other question with the multiple objects in the view for the device stuff. Florian, hopefully I didn't butcher that, but if you want to ask that question on Discord, we could probably have a further discussion on that one as well.
Absolutely. Yeah, I think we ended up not covering everything. So what we realized is that the schema topic is much larger than what we initially thought. So talking it through takes quite a bit of time, but yeah, we're at the top of the hour. We're over the top of the hour. So this brings this session to an end. Hopefully it was useful, and maybe we'll cover some of the remaining topics here in one of the next sessions. Thank you. Bye.